Hi, today we're going to be talking about nuclear stability. What causes some isotopes to be radioactive, whereas others are stable. And just to begin with, I want to talk to you guys just real fast, establish some groundwork and some basic vocabulary. Okay, so first of all, atomic nuclei, all right, are composed of nucleons, which is a particle in an atomic nucleus, and it's either a neutron or a proton. Now, a nuclide is the general term applied to the nucleus of each unique atom. All right. And it is specified by the mass number. All right. So the total number of protons and neutrons in the nucleus of a given atom. Remember, that's what mass number is. And a neutron is a subatomic particle that doesn't have a charge. Protons have a positive charge, but when you add them all up, those give you the nuclide. And basically, you designate it for the most part just like you would with any other isotope. But the term nuclide applies only specifically to the nucleus. We're not going to be worrying about electrons at all, really, this little mini unit that we're talking about when we're dealing with nuclear reactions. Nuclear chemistry is all about the nucleus, and that's why we're going to be using these terms. Remember, an isotope, there are atoms with the same number of protons, but with different number of neutrons, and therefore different mass numbers. All right? They have different mass numbers. All right, now, if the nucleus, which is often thought of or imagined as a bunch of spheres being held together. I'm sure you've seen pictures like this. Some of them are protons, some of them are neutrons. But if you think about it, the main force that we know of in atoms is the electrostatic force. That's that whole force that opposites attract and like charges repel. Well, if you think about it, if inside a nucleus all you have are protons and neutrons, protons are all positive. Neutrons don't have a charge. Shouldn't the protons repel each other like two opposite magnets? And the answer is yes, they do repel each other. However, they're still held together inside the nucleus. So the question is, what's holding them inside the nucleus? I mean, they should fly apart since like charges repel. What holds them together is another force, a stronger force called the strong nuclear force. It is a force of attraction between nucleons that hold the nucleus together despite electrostatic forces of repulsion. Okay, so they want to be pushed apart because like charges repel, but the strong nuclear force holds them all together. Okay, holds them tightly together. Now, key things are two things. One, it is very powerful, but only over very short distances. How short? Well, basically about as short as an individual atom would be. Okay. But the larger the atom, the greater the distance between one proton and another, the more it's going to, or the weaker that force is going to be. Okay? So it's also known as the binding force because it holds the nucleus together. Now, what causes it? There's different interpretations. Could be duct tape. You never know. But we don't know for sure what causes it. We do know and we can measure its effects, though. All right? Now, the strong nuclear forces causes the nucleons, all right, to have less potential energy while together in the nucleus than they do while they're loose. All right? So they have, and we think about it, potential energy. Right now, as they're together, they don't have any energy, let's say. But if you hold one apart, because it wants to fly back in, it has now some potential energy because it wants to fly back in. All right. Now that means, of course, and we learned this first semester, the nucleons are more stable together than they are separated. Remember that whole inverse relationship between potential energy and stability. The more energy a system has, the less stable it is. The less energy it has, the more stable, like on a ladder. If you're standing on the bottom rung of a ladder, you don't have a whole lot of potential energy. You're not that far off the ground, but it's pretty stable. It's hard to fall off and hurt yourself. But if you climb all the way up to the top and are standing on the very top, which, by the way, never do because only idiots do that. If you stand at the very top, you have a lot of potential energy. You're really far off the ground, but you're not stable at all, okay? You're not stable at all. It's easy to fall off. So hopefully you remember that when you're thinking about the relationship between stability and potential energy. Now, nuclear binding energy is the energy that is released when nucleons that are separated come together to form a nucleus, okay? So because they are separated, they have more energy. They come together, they have less energy. And it releases that energy when they come together, all right? So it is also, think about it in the opposite direction, it's equal to the amount of energy required to break a nucleus into individual separated nucleons. So I got to put energy into the system to break it apart, and energy is released. Oops, energy is released when they come back together. All right. And using terms that we learned before, endothermic, remember energy going into a system. It's endothermic, energy is required to separate the nucleons, but it's exothermic, energy being released when the nucleons come together to form the nucleus. All right, very important. It's a two-way process. Okay, so if you're going this direction, the nucleons are separated, then they're going and it produces energy. However, if you want to go in the opposite direction, then energy has to be added to the nucleus in order to separate them out. Okay, so it goes both directions. Now, this is where things get weird. Nuclear chemistry is quite weird, okay? For reasons that I'm going to talk about. Nucleons have a smaller mass when they're part of a nucleus than they're separated, okay? This is really flippin' weird. So let's say this is a proton. When it's part of a nucleus, its mass is slightly smaller than it is when it's separated. All right, just to give you an idea of how this, to give you something to equate to, let's say you go to a supermarket and you want to buy 10 apples, okay? And let's say for whatever reason, because you're, OCD or something, you want each apple to be the exact same weight, all right, the same weight. So you go and you get an apple and you put it on the little scale. And let's say it's a metric scale. So instead of in pounds, it measures it in newtons, which is the unit of force or weight in the metric system. So you find 10 apples, you weigh them individually. Each one weighs exactly 1 Newton, all right? So you put one in, 1 Newton. Take another one, put it in, 1 Newton. And then you take all 10 apples and you put them in the basket at the same time, and it reads 9.6. And you're going, wait a second. You go back and you measure each one. Each apple separately is exactly like 1.0 newtons. But when you put them all together, all 10 of them, instead of being 10 newtons, they have a smaller mass. It's like 9.6 or whatever. That's what happens with nucleons. They have a smaller mass when they're together than they do when they're separated. Now, this mass difference is known as the mass defect, okay? And this is where the binding energy comes from, all right? This is where all of the energy, when you hear about nuclear reactions, you think of atomic bombs or nuclear power plants. The amount of energy in these reactions can be incredibly large, much higher than a chemical reaction could be. That's why, I mean, just one, from history, if you remember the atomic bomb that was dropped on, Hiroshima towards the end of World War II, it killed like instantaneously, something like 30,000 people. And that bomb was something along the lines of like 100 to 1,000 times more powerful than the best bomb that we can produce even today using chemical reactions. And the weapons that we have today, oh my goodness, are again maybe 1,000 times more powerful than the one we dropped on Hiroshima. And all that energy comes from that mass defect. All right. And the reason, the way to calculate it is something that Einstein theorized in his theory of relativity. He came up with this equation in order to measure this amount of energy. This is this famous equation, E equals mc squared. Okay. E represents the binding energy. That's this thing right here. M for mass, well, that's the mass defect. That is how much difference there is between when the particles are separated and when they're together. And c squared, c represents the speed of light, okay? And when you square it, you get a really huge number. Now, the concept is, because one way of thinking about it, because the strong nuclear force is so strong, the particles go so fast when they come together that they are accelerated, parts of them at least, are accelerated to the speed of light. And basically, the only thing that can travel at the speed of light is energy. Therefore, the matter, when you accelerate to the speed of light, it becomes light, it becomes energy, and you are actually creating energy. This goes against the law of conservation of energy, which says that energy cannot be created nor destroyed. Once this was developed, once nuclear chemistry was developed and discovered, they had to change that law. Now, the law says that energy cannot be created or destroyed in a chemical or physical reaction, but it can be in a chemical one. Same thing with the law of conservation of mass. It says that matter cannot be created nor destroyed. But here it is. You see that mass defect? That matter, when it's coming together, technically is being destroyed. And it's turned into energy. Just like when you put a whole bunch of energy in it in order to separate it, some of that energy gets slowed down, as it were, and you create mass. That's why you get more mass when they are separated. I know, right? Just mind-blowing. But this is some pretty serious stuff that I'm laying on here. But this is why, those atomic bombs and atomic nuclear weapons are so scary. It's because they do produce such a high degree of energy. And also why nuclear energy is so enticing. Right? When you have a nuclear power plant, either to create electricity or one to move a large naval ship like an aircraft carrier around, it uses a huge amount of energy. Is required, and those nuclear power plants on those ships can produce that high degree of energy. All right. Now, the last thing we're going to be talking about is this concept of nuclear stability. Now, some atoms, all right, some isotopes are more stable than others. Okay. And one indicator of this nuclear stability, and by the way, remember, things that isotopes that are unstable, they are radioactive. Okay, they release energy. We'll talk more about that in the next lecture. But the binding energy per nucleon, when you figure out how much binding energy it has, and you calculate how many nucleons you have, that's one indicator. Now, the greater the binding energy, the more stable the nucleus is. If you think about it, more energy needs to go in to break it apart. So the greater the binding energy, the more likely it is to not break apart and therefore to remain together, and it therefore means that it's stable. All right. Now, because the strong nuclear force only works over very short distances, the larger the nucleus, the weaker that strong nuclear force is, and therefore the larger the nucleus, the less stable it is. So basically, really large nuclei are unstable. All right, because this is a small nucleus and the particles are really close together. This is something like, I don't know, we got about maybe 10 or so nucleons. So it has a mass of about 10. The largest atoms, the nucleides, have upwards along the lines of 250, all right, 260, 270 atomic mass units in mass. So, I mean, those things are huge. And because they're so large, imagine one of these like taking up the size of a beach ball, all right? Then one proton over here compared to one over here is so far away that the force of repulsion between those two becomes greater than the strong nuclear force holding them together, and they fly apart. All right. So they're just keep in mind the largest size you can have for a stable nucleus is going to be 209. Once you get larger than 209, there are no stable nucleides. Now, that's one reason for nuclear instability is large size. Another cause is the ratio. This is something that you should have looked at when you did the gizmo on isotopes. And the ratio of neutrons to protons is also very important for nuclear stability. For various reasons I don't want to get into because I don't want to bog you guys down, the ratio of 1.1 neutrons to protons. In other words, you take the number of neutrons and you divide by the number of protons. The closer you are to a 1.1 ratio, the more stable it is. Once you get like too many neutrons and the ratio goes above that, or not enough neutrons and the ratio goes below it, that also will cause a nucleus to become unstable. And that's it for the causes of nuclear stability. Thank you very much.